Hi everybody, welcome back to your regularly scheduled programming. Today we're solving LeetCode 543, which is called the diameter of binary tree. The question asks us, given the root of a binary tree, return the length of the diameter of the tree. The diameter of a binary tree is the length of the longest path between any two nodes in a tree. This path may or may not pass through the root. The length of a path between two nodes is represented by the number of edges between them. On the whiteboard, I've drawn out the first example we're given from LeetCode, which is this binary tree right here. The output for this is supposed to be 3, and the paths we can take to arrive at that solution is either 4, 2, 1, 3 or 5, 2, 1, 3, where these numbers represent the actual node and the arrows between each node represent the edges. So the first path is 4, 2, 1, 3. If I go from nodes 4 to 2, that's one edge, 2 to 1, that's our second edge, and 1 to 3, that's our third edge. So we have 3 edges, which is the correct diameter. I could also do 5, 2, 1, 3, which is very similar. So 5 to 2 is edge number 1, 2 to 1 is edge number 2, and 1 to 3 is edge number 3, and our diameter is 3. So just think of this as the longest path we can take, or the max amount of edges we can take to get between two nodes. In this case, we're getting between node 4 or 5 to node 3. That's the longest path we can take between any two nodes, and there's 3 edges involved in that path. Cool. We can also approach this similarly by calculating the left and right depths of the subtrees. So for this root of 1, the left subtree is going to be 2, 4, and 5, and the right subtree is going to be just a single node of 3. The depth of any tree or subtree is just how many nodes deep does it run. So in this case, it runs 2 nodes deep, so we have a depth of 2, which I've written out here. LD represents the left depth, RD represents the right depth. On the right subtree, we just have a single node of 3, so that's just a single node involved, and the depth of that's going to be 1. If we then take the sum of these left and right depths, well, then we arrive at 3. So 2 plus 1 is 3, and that's the same as our diameter. And we can test this out with a few more just to make sure it works. Our next tree is this tree right here, 1, 2, and 3. The output for this is supposed to be a diameter of 2, and the path we can take to get to that is 2, 1, 3. Or we can take it in reverse, so 3, 1, 2. If we do our depths approach, then the left subtree is just a single node of 2, and the right subtree is just a single node of 3, and the depths for each of these are just 1 because they run 1 level deep or 1 node deep. It's a single node. So if we take the sum of our left and right depths, that's 1 plus 1, that's 2, and our diameter is 2, so that checks out. Next, let's look at this tree right here where we're just branching out on our left side. The diameter of this is supposed to be 1. And we can take paths of 2 to 1. We have 1 edge involved, and that's the longest path we can take. Our left depth for the left subtree is just going to be this left subtree of 2. That's a single node involved, so the depth is going to be 1. The right subtree in this case is empty. There is no node, so the depth of that's going to be 0. If we take the sum of that, 1 plus 0, it is 1, and that's our diameter. Finally, let's explore if we have no children and it's just a single node. The diameter of something like this is just supposed to be 0. And that's because we have nowhere to go. In all these other cases, I had arrows pointing to like the next node. So in this previous one, we went from 2 to 1, right? Here, we have nowhere to go. So I've just drawn out the 1, but there's no arrows, nowhere to go. So we're going to be given a diameter of 0. And we can confirm this with the depth calculations. So the left subtree here is just going to be an empty tree, which is going to have a depth of 0. And the right subtree is also going to be an empty tree, which has a depth of 0. 0 plus 0 is 0, and our diameter is 0. Now that we have a firm grasp of what's going on here, we can implement our strategy, which is going to be just calculating the depth of each subtree and updating the diameter accordingly. We're going to be implementing this recursively, and the example we're going to do is just what we had here as the first LeetCode problem, and we know what to expect. First step is going to be initializing the diameter to 0. Then we're going to be making our left and right recursive calls. So first recursive call is going to be this left side of 2, 4, and 5. That's going to then make its own recursive calls on the left and right subtrees of its tree, which is 4 and 5. Then this can recurse even one level further to the empty trees, because keep in mind that this node 4 still has left and right children, they're just null or empty. So in the event that So when we go down to that level, this is when our base case is going to activate. Because remember that an empty tree is still a binary tree. It's still a valid binary tree. It just has a depth of 0, and that's what we're going to return. So if we're given it, that's going to be our base case. If we have an empty node or empty tree, we're going to return 0, which is representing the depth. Now we can send this back up the call stack to this most recent call, and we can calculate the diameter is just the sum of these left and right depths, which is 0 plus 0, and our diameter is 0. We'll also calculate the depth, and we know from before that is just how many levels does the tree run deep, or how many nodes, and in this case it's just a single node of 4, so the depth is 1. Similarly, we have the exact same situation with the right subtree, where it's making the left and right subtree calls of null or empty. They'll return 0, and then we can calculate the diameter is just 0 plus 0, which is going to be end up 0, and then the depth of this is also 1. It's just a single node. Now that we have those, we can send that back up the call stack and calculate our diameter for this tree. And for this, it's going to be the depth of the left and right subtrees, so depth of 1 plus 1, and we have a depth of 2 now, or I mean diameter of 2, sorry. And now that we have that, we can update our diameter up here to 2. We'll also calculate the depth, and that's just, we know that it runs 2 levels deep, so that's also 2. Now we can explore the right subtree. It's just a single node of 3 that'll recurse into the empty subtrees. The left subtree is going to return 0. The right subtree is going to return 0 because our base cases get activated when it's a null or empty node. We'll send that back up the call stack. Our diameter here is going to be 0 plus 0, which is just 0. And our depth is just similarly what we had here, 1, because just one node. Now that we have both the left and right subtrees explored, we can send this all back up to the original function call and calculate the diameter for the final tree, and that is just going to be the sum of the left and right subtree depths. So for the left subtree, we had a depth of 2. For the right subtree, we had a depth of 1. 2 plus 1 is 3, so we can update this to 3. And that's what we're going to return. And that's our answer. So now that we have all this, we can come up with a coding solution, which I'll show you in a second. Here is the code to our solution. So we're going to have a function called diameter of binary tree that's going to take in the root of the tree. We'll initialize a diameter variable to 0. We'll then create our helper function called calculate the depth, which is going to calculate the depth of any subtree or tree. It'll take in a node and is going to check first the base case of if we don't have a node, which means it's an empty tree, then we'll return 0 because an empty tree can't have a height. Or a depth, sorry. Next, we'll make the left and right recursive calls, calculating the left depth and the right depth. We'll then update our diameter variable and set it to whichever is bigger between the current diameter, which is going to be calculated between the left depth plus the right depth, or what we currently have set as our diameter. Finally, we'll be returning 1 plus the max between our left depth or our right depth. This part may be a bit confusing, so I'll run through this real quick. Basically, think that we're calculating the depth for a single node right now. Let's say we're just given the node 4 that we saw on the whiteboard. The left depth and the right depth for this node 4 is going to be 0 because they're going to be the null trees respectively, right? So to calculate the depth of this node 4, well, we know intuitively that it has a depth of 1, right? Because we mentioned that the depth is how many nodes is present or runs deep in the tree. And for a single node, it's going to have a depth of 1. But this math.max of the left depth and the right depth, that is going to yield 0 because both of these two subtrees are the empty subtree and they'll have evaluated to the base case of returning 0. So we're going to have to manually account for this node and every current node by adding this 1. So we'll be manually incrementing basically the depth that we're on. We'll then calculate the depth of the entire tree, by passing in the root to this helper function we made. And then finally, we're going to be returning the diameter. Keep in mind that when we make this function called to calc depth on the root, it will actively be updating the diameter, and by the end of it, we can have a final diameter that we can return. I'm going to run this now, and it's going to pass our test cases, and now we can submit it. Wonderful. Final thing I want to discuss is the time and space complexity. So our time complexity is O of n, which is linear, and this is because we visit each node once during the traversal. Keep in mind that the n represents the number of nodes in the tree, and since we basically traverse every single node in the tree at least once, or I mean exactly once, we're going to have a linear runtime. Our space complexity is also going to be O of n, linear, and this is because the depth of the call stack can be equal to the number of nodes in the tree if we have a completely unbalanced tree. So if we have a tree just like branching on one side only, basically a linked list, then it's going to make the recursive calls on all of those. It's going to create a call stack of the number of nodes that are present in that tree. And that's going to be, in worst case, O of n. Thank you for watching this video. I hope it helped, and I'll see you in the next one.